for example, the bomb tester and the quantum eraser setup, which are just used with a laser. They're sort of just analogy kits. And the one that Farbad just mentioned is actually one of our most popular ones, the quantum crypto kit. And the whole point of this is to really play through the entire BB84 protocol. So you have Alice as a sender, you have receiver Bob, and then you have an eavesdropping unit in between. And you can really play through all of the steps, you know, bases and bits and generating a key between Alice and Bob. And then once the students have understood the principle, you put in Eve, and you can really see how her presence is inevitably revealed. But as I said, those aren't real quantum kits. You know, this one, for example, uses a pulsed laser. And so we always wanted to have the real deal, so to say, and this is the result of that development. This is our quantum optics kit. I will walk you through what you're seeing here. I will show you the beam path and talk a little bit about what you can do with it. So we're starting out with a 405 nanometer laser. We go over 2 alignment mirrors, a half-wave plate to set the polarization. Then we hit a nonlinear crystal, namely BBO type 1. This is where the magic happens. So here's where we generate photon pairs. Then after the crystal, the pump laser isn't needed anymore, so it's collected down here by beam dump, which serves as a really good help for alignment as well. As I said, the BBO generates photon pairs, and they exit the crystal at a certain angle. And down here, we collect them with those 2 single photon detectors. You can see here, we do not fiber couple that. You know, if you've ever seen students couple light into a fiber, that's sometimes painful to watch. But also, we like to just have the detectors in the place where the actual measurement occurs. Because in teaching, you know, we emphasize this importance of the measurement a lot. So just having the detector fiber coupled somewhere on your shelf didn't feel like a good teaching choice. So just say, here's your detector, here's where your measurement occurs. Now, for a couple of measurements, we place a beam splitter here. So part of the light is guided down here to this Michelson interferometer, which is placed on a separate board. So if students, for example, if they want to work in pairs or in groups, one group can have the assignment of aligning the Michelson while the other one sets up the pair source. Or, you know, if you want to manage your time in your lab course, you could have this pre-aligned already somewhere. Now, at the output of the detector, at the output of the Michelson, there's a third detector, and all of the data collection and processing is done in this education-grade time tagger. Now, as I pointed out, it's really important for us that students can align all this themselves systematically, and so obviously there are a couple of alignment tools in the kit as well, and together with the 150-page manual, that should be enough to get everything where it should need to be. Now, I want to acknowledge the collaborators that we've been working with, namely Kim Weber and Rüdiger Scholz from the University of Hanover. And this is really good news for you. So we really like to work with collaborators, and it's good news for you because a lot of their teaching philosophy and a lot of their teaching experience went into the kit. So this is really tested in a real life lab course environment. I don't have the time to go into everything in detail, obviously, in this half hour. So if you go to the kit's webpage, there's a tab called Experiments, and there you see all of what you can do with the kit. So it's quite a lot. I will only be able to touch the surface a little bit. So I invite you to look at this in detail. Also, there's a link to a webinar that I recorded about a year ago. So there's more information in there as well. Now, I talked about the BBO here generating the photon pairs, and it's really important to measure those pairs, really measure them as a pair, so to say. So we place single photon detectors here, namely our SPDMA. Those have been released about 2 years ago by Thorlabs. And to the best of my knowledge, they're the smallest ones that you can buy out there because, as I said, we really wanted them in the setup. And the way that we distinguish the photon pairs from other events like stray light, for example, is just by timing. So when detector T makes a click and A makes a click like 2 nanoseconds afterwards, then we say, okay, that's probably the 2 photons, right? If the detector A clicks like a microsecond afterwards, then yeah, that was probably stray light or a dark count event. And so The coincidence window in our setup is normally like 5 nanoseconds. Everything within that is counted. Everything else is discarded, which is why it's especially suitable for lab courses, because a lot of the stray light is not a problem at all. Now, the most important thing that I feel like students need to understand is what's the difference between a classical and a non-classical light source? How do I measure that? Assume you have a black box where there's a hole cut in it and you just have light coming out. How do I know if it's classical or not? And the way to do that is by introducing a beam splitter here and placing a third detector at the output, so that's called the Granger experiment. And, if you're really understanding the principle isn't really difficult, because, if I'm really picturing a photon as an elementary excitation of the electromagnetic field, I can't cut it in half, right? So detector A will make a click or detector B will make a click. If those two click at the same time, something's fishy. So that's an indicator for non-classical light source. And the way that single photons transmit or reflect, and you can pour that into mathematics. So this is called the second order autocorrelation function. Fancy name, but in the end, you just plug in all of the count rates that you see here. So the pair count rates between T and A, T and B, the triple coincidences, which means exactly that A and B click at the same time. And what you get as a result is just a number. But that number tells you about the nature of the light. So if it's 1, you have a coherent state, meaning a laser. If it's larger than 1, you have classical light, like a light bulb or an LED. And if it's smaller than 1, then we really have a non-classical light source. And in our experiment, we reliably get below 0.1. So once students have understood what that signifies, then you can go on and start experimenting with single photons, meaning, for example, you could put in a polarizer and observe how single photons behave at a polarizer. And what you see here is a screenshot of our software. We always have 2 plots like this. The upper one that you see here, what I've plotted is the coincidence count rate between the trigger detector and B over the polarizer angle. So you're rotating the polarizer and you're collecting the count rate. And at the same time down here, we always measure this autocorrelation function, meaning for every data point up here, we have one down here. And as you can see here, we're well below this classical limit of 1. So what this means in combination is that this is really single photon physics happening. The code itself is free, so it's open source, because we expect a lot of people just to take the kit as a starting point for their own experiments. So we wanted it to be easily extendable. Next one is my personal favorite, single photon Michelson interferometer. So you place another beam splitter here, you have a mirror here and here. At the output, you place the third detector. You put one of the mirrors on a piezo stage. And yeah, as you can see here, so that's the setup. So we have the 2 detectors from before. You align all of this. If you've asked yourself, how do I align this? Because I don't see the 810. We've made sure that there's a good way to do this by using a visible alignment laser. And so you just place a lens here, you align everything. So I have the beam splitter here, the mirror on the stage, and the second mirror. And then you replace the screen here with a detector. And what you see here is, again, a screenshot of the software. I'm plotting the coincidence rate between the trigger detector and B. So I'm recording the output of the Michelson over the stage position. So I'm moving my mirror and I'm observing the count rate. And as you can see here, this is what you would expect from an interferometer. And at the same time down here, we are collecting the data for the autocorrelation function. And again, well below classical limit of 1. So those 2 in combination mean that even single photons exhibit interference, right? Superposition of single photon states. And I'm sure that many of you are aware that this works, right? So I'm sure that if I told you that a single photon interferes with itself, none of you will fall from their chair. But the cool thing is, if you're ever asking someone, have you ever seen an experiment? 95% of physicists will say no. And we talk so much about photons and photon scattering on atoms and being absorbed in whatever, but it's really interesting how few people have seen real single photon experiments in a lab. Okay, now the last experiment in the kit, sort of the great finale, is the quantum eraser. If you're not familiar with that, I take a little detour. Picture a double slit with electrons, right? And you're shooting electrons at it. You're seeing interference behind the slit. And if I'm asking, dear electron, which of the two slits did you take? Which one did you pass? Then my interference breaks down, because essentially I'm asking for a particle property, like a defined way. And so I don't see a wave property anymore. There's an optical analog to that. So again, I'm having the sketch of my interferometer here. And if I place two perpendicular polarizers in the interferometer arms, then I have marked my path. I have path information. Why? Because I could just measure the polarization at B, and my system would give me an answer of 0 degrees or 90 degrees. And just the fact that I could measure that is enough for interference to break down. And the great thing is I can get that information, I can erase the path information, hence the name quantum eraser, by introducing a polarizer with 45 degrees. And every photon arriving at the detector will, by definition, have those 45 degrees, and I see my interference again. And this is how it looks for the setup. So in my interferometer now, I've placed those polarizers here, and this is the measurement. So I'm looking at the coincidence count rate, again, behind the interferometer over the stage position. The blue curve is essentially what we've seen before from the Michelson. So if the two polarizers are parallel, I will see just standard interference. If I'm rotating one and I have orthogonal polarizers, then I get the red curve here, so no interference. And then finally, I'm placing this last polarizer here with the 45-degree orientation, and I get the green curve, and I have my interference back. So that's kind of a cool experiment. Now, one of the things that when you talk to people that are not at home in quantum optics or just students, they will have one very, very prominent misperception, namely that light is essentially just a barrage of photons. So you have your laser here, and I can picture photons. I can picture that like a stream of photons. And in that mental image, it's kind of natural to say, oh, can't I just take out all of those little cannonballs that are flying there? And eventually I will be left with one, right? That would be an intuitive picture that unfortunately a lot of people have. And it's not that simple. That's the whole point that we want people to learn. And we just say, just measure it, right? Just verify experimentally that this is not the case. So what you have to do is, again, you measure the autocorrelation function. So you take the alignment laser that's in the kit anyway, you shine it onto a beam splitter that has a strong ND filter attached, and then you have, again, the single photon detectors in transmission and reflection, and then you just measure, and, well, surprise, surprise, you get G2 equals 1, meaning coherent light and certainly no quantum optical light source. And when you're going a little bit more deeper into theory, well, this essentially, well, the reason behind that is that when we talk about single photons, what we talk about is a Fock state with a defined photon number, whereas a coherent state is a distribution of states. And if I'm just attenuating my light, I'm scaling this distribution, but it's always going to be a distribution. There's never going to be this defined photon number. And so, yeah, it's important for students to really understand that this picture of this light as a barrage of photons is just not applicable. Now, I talked or emphasized at the beginning that we want students to align this themselves. And I'm going to show you how we ensure that in the kit. We use a little trick. We actually use many tricks, but the most prominent one is the use of an Axicon. What is that? Essentially, you shine light on it and you generate a cone of light from it. So when you place your screen in front of it, you see really a circle. If I'm moving the screen further away, the circle will become larger. If I'm moving it closer, the circle becomes smaller. And now it won't surprise you that we tailored the opening angle of this Axicon here to match the opening angle of the photon pairs. So we can do all of the alignment with this visible class 2 laser. And as you can see here, we can place our, for example, detectors based on that Axicon. Again, this is the coarse alignment. There's a step for fine alignment that I won't go into detail now, but this is really helpful because you can see what happens. You can place your elements accordingly. There's a few additional experiments that I want to show you. As I said, we try to build it as open as possible. We have the setup open, we have the lab view software open, so it's easy to extend. And I'm going to show you 3 extensions. First of all, you can literally turn the setup into a 2-bit quantum computer. What do I mean by that? So you can actually implement the Deutsch algorithm. All you need are 2 liquid crystal wave plates that you place in the interferometer. And now it's really important for me to manage expectations. So it's not like I'm factorizing 21 with this, right? So those of you who don't know the Deutsch algorithm, it's literally the simplest quantum algorithm that you can find. When you're looking it up in the Qiskit documentation from IBM, it's literally the first algorithm. So it's not about really what's the result of the measurement. The point of this, the teaching value of it, is to have something in your lab. So you talk about qubits, you talk about Hadamard gates, but you always talk about it on a blackboard. And this gives you the option to have it in your lab and just point at an optical element and say, this is your Hadamard gate, right? So this is what the teaching value of this is. Next thing, you can actually implement the single-photon double slit. So this is something that's not yet in the manual. The optical quantum computer extension, we discussed that in detail in the additional experiments section in the manual. The double slit is not in there yet. We will add that in the next months. And it's quite simple, actually. So you just have a double slit here. You place a slit in front of detector B. When you're thinking about it in more detail, it becomes apparent that it makes more sense to scan the slit here rather than scanning the detector. And then you arrive at this. So I'm plotting the coincidence count rate between T and B over the slit position here. And as you can see here, there's this clear interference pattern of a double slit, which is, yeah, really cool, because now you can finally teach about that, because we all, the double slit is so often used as a picture and as a teaching aid when talking about the behavior of single photons. Finally, polarization entanglement. So I was probably a little fast at the beginning, and then not everyone will have realized it when I said that we're using a type 1 crystal in the kit. This crystal generates time energy entangled photons, which is essentially a fancy way of saying that I have these pairs. We do not generate polarization entangled photons. That's a deliberate choice for 2 reasons. First of all, those crystals generate different count rates. So you get better count rates just with a type 1 crystal. And when you're doing a teaching experiment, it's always a little better to have more count rate, because your students may misalign something slightly, and having a bit of play there is really helpful. And the second thing is, I feel like it makes sense for them to learn about all of the fundamentals first before going sort of to the top shelf of physics and dealing with polarization entanglement and what that signifies. So it was a deliberate choice to use the type 1, and we always had in mind that we're going to do an add-on kit. And this is something that we've almost finished developing. As I said, you need a different crystal. We use a type 1 crossed, which just means you take 2 type 1, rotate one by 90 degrees, put them together. And that crystal generates polarization entangled photons. And then you can measure Bell's inequality. What you need to take care of is pre and post compensation. So you need additional crystals to make sure that everything works really well, to get good values. What I'm showing you here is sort of the results of our prototype measurements. You're seeing the so-called S value, that's the Bell value. The classical limit is 2, so everything above 2 is a violation. And the maximum, the theoretical maximum, is 2 times square root of 2. And I'm plotting this S value over our iris diameter. So we have in front of our detector, we have this little iris. And what you see here essentially is that even if I'm opening my iris, the entanglement quality doesn't go down. So I'm collecting polarization entangled photons over quite a large angle. And in the end, when you have it fully open, we collect about 6 kilohertz, and that's good value to perform experiments with. What's really cool about this is that the alignment procedure of our quantum optics kits, or the base kit, still works. So this is how we had hoped it would turn out, that you can go through the basic experiments with the students, and then once they've understood that, you just take out the crystal, you put in the pole entanglement crystal, you add those pre and post compensation crystals with not a lot of effort to align them, and then you can perform the Bell measurement. That's quite cool. We're also going to add in the manual a little passage about the E91 crypto protocol that you can do with entangled photons. We're going to add state tomography. It's going to take us a little bit to release this, so we plan on releasing this in October this year. Price is going to be about 4 to 5K. Again, it's just the sum of the components. Right, so that brings me to my last slide. The price is always something that people ask. You probably know that Thorlabs is very open with pricing. So the kit comes in at about $34,000. The board is another 1,000. So in the end, it's about 35,000. Again, just some of the components. Main cost drivers, obviously the single photon detectors, but you have everything in there that you need. So that concludes my talk. I'm very happy. If you have feedback, ideas for extensions or questions, just send me an email or just hit me with your questions now.
Thank you so much. Thank you. So that was really nice. So I really, can you still hear me?
Yep.
Oh, this is a bit loose. Okay. So you see the people here. So if anyone has any question, Dr. Klauser, what do you think about this experimental? So Dr. Klauser said that. Dr. Klauser said that. Dr. Klauser said we wish to have this in 1972.
Yeah, I guess so.
Yes.
Isn't the saying we stand on the shoulders of giants? I mean, obviously this is only possible because of so much of work from previous people.
It's just a connector issue. Okay, some connector issue again. Sorry, 1 second. Okay, I think you're back. Hello?
Yep.
Okay, thank you so much. So yeah, and also you didn't talk about the quantum cryptography. If you want to learn quantum cryptography, I really recommend the kit, which is not 33,000, is about 4,000. I think it's over 4,000 now. When I bought it, it was cheaper. Yep. And thank you very much. So any question? Quick question? Yes. Is there a student discount? Student discount? A student student discount? I don't know.
So if you want to buy it for you at home, then maybe for universities, no. Because the point is, as I said, we spent, I think, like 3 person years went into developing this, and even a lot more money because all of the parts that we needed. And you get this just for the sum of the components. So I'm hoping that I could make you understand that this is really a very good value proposition already, and we can't really go down in price with a lot.
Another thing we can do is, because I already have it and he's our students, I can just rent it to him, get $100 and he can rent it. How about that? Okay.
Sounds good.
Okay, any other question? Thank you very much. I think we are a little bit behind because of the technical difficulties I had. Sorry about that. And thank you so much. I know it's very late for you in Germany, and thank you for joining us and telling us about this equipment. These are really useful for education and learning. Thank you.
You're welcome.